Welcome to Lecture 6 for Chemistry 702. This lecture is on radioactive decay kinetics. Additional reading for this lecture can be found in the books Modern Nuclear Chemistry, Chapter 3, and Nuclear Radiochemistry, Chapters 4 and 5. This lecture will cover radioactive decay kinetics. We'll go over some basic equations. We'll utilize those equations, talk about mixtures, equilibrium, branching. And then we'll also discuss natural radiation and relate that to radioactive dating. This lecture will also include some programs that can be used, some that you can write yourself, which may be assigned as homework at the end, and then a program that can be used for doing Bateman calculations. Radioactive decay obeys a few simple rules. The number of radioactive nuclei that decay in a radioactive sample decreases with time. This decrease is exponential, as we showed on the previous slide. And unlike chemical reactions, this rate of decrease is independent of pressure, temperature, mass action, and it follows first-order kinetics, so it's actually fairly easy to model and understand. There are some decay methods, such as electron capture and internal conversion. Since this involves atomic electrons, they can be affected by the chemical conditions, but the decay constants themselves don't change. It's just the probability of the electron being available for the reaction to occur that changes. These decays are specific for an isotope, and they're irreversible. Decays only go in one direction. The decay of a given radionuclide is random. If I have a number, or if I'm following a single radioactive isotope, I can not predict when it decays, but I can have a probability of it decaying. And the decay rate is just proportional to the amount of the parent isotope. And this is observed through this decay constant times the number of atoms is equal to activity. So the rate of decay is equal to the decay constant times the number of radioactive isotopes. This is a very fundamental equation that we'll use. And this decay constant, that's just equal to log 2 divided by the half-life. And the decay constant is the average decay probability per nucleus for a unit time. And the decay constants, as we talked about in the first chapter, is the units are in inverse unit times. We'll go over some basics of decay equations. Basically, the only factor that's important for radioactive decay is the length of time in which I'm going to observe whether or not the decay occurs. This probability of decay, P, is equal to the decay constant times that time interval that I'm using. So the probability of an atom not decaying is 1 minus the probability. So 1 minus P is equal to 1 minus lambda delta T. Now if I extend this to a probability that an atom will survive n intervals of this time, I get the equation that's listed here. Now if I take the limit of this equation, and the limit is expressed here as n goes to infinity, I have a generalized equation. Let me apply that to our decay constant equation. I have this term, and now my equation of e to the x becomes e to the minus lambda t. That's my limiting value. And if I consider some n naught listed here, n naught being the initial number of radioactive atoms, the fraction that remains unchanged after time t is provided here. N is the number of atoms remaining after time t, and this equation is a fundamental equation that we will use throughout our radiochemistry course. A straightforward route to evaluating statistical and average behavior during radioactive decay is through utilization of binomial distribution equations. And we're going to go over this in the next few slides, and what we're going to get to is a way of evaluating error from the number of counts that you have in during radioactive decay. Right, so we know that radioactive decay is a random process. The number of atoms that decay in a given sample will differ for the same delta t. So in other words, if I count a sample for a relatively short period of time, shorter than the half-life, often many orders of magnitude lower than the half-life, and neglecting large time differences between when I do these measurements. Even though I may measure a sample for the same amount of time, I could get slightly different values occurring. And in a lot of ways, this can be modeled through binomial distribution. And this is a reasonable process to describe radioactive decay. As an example, you can bin counts, measure number of occurrences that fall into those bin numbers, as was shown here, for a figure of frequency versus number of counts for radioactive decay. And this model is used as a basis for describing the behavior of radioactive decay. Binomial distribution, the classic description, is with a coin flip. So if we have some probability, we're going to call this here px, of obtaining so many disintegrations in a bin during time t, as long as t is short compared to the half-life, that's just going to vary based upon the number of trials and the probability of the event in that bin. And we're going to use the equation we're going to use is described here, where all we have is just the number of trials and the probability of that event going into that trial. And x is obtaining so many disintegrations. What this application of this equation shows us are typical binomial distribution patterns, which are provided here. As we discussed earlier, the probability of an atom not decaying in time t is 1 minus that probability of it decaying, and the equation that we use is provided here. We can take the terms from this equation and expand that into our binomial distribution for radioactive decay and pull in terms that actually are relevant to a given decay process, including the time, the decay constant, and the number of initial atoms. There's also a way of evaluating a time interval between disintegrations. So if we have a certain disintegration and we're wondering what's the time interval between that disintegration and the next one, we can actually talk about the probability, which is listed here. And again, this is written in terms that are specific for radioactive decay, where we have the number of initial atoms, the decay constant, and the time. And we write this probability between t and t plus d as p t dt. Now we can also talk about what's the average disintegration rate. This is a little bit more important for understanding statistics. We can describe an average disintegration rate based upon an average value of a set of numbers that obey binomial distribution. Since radioactive decay can be modeled on binomial distribution, these equations work pretty well. So we can use, and here we have some of the equations. We take this binomial distribution equation, and we're going to replace it with something related to disintegrations. What's the average number of disintegrations? So let's talk about those R disintegrations. And this average value, so here's our binomial distribution. We've replaced some sort of probability with disintegrations. Our average value for these disintegrations is listed here. R average is equal to the sum of R times the probability of R, and that gets expanded into this term here. We can solve this larger term using binomial expansion term. And the binomial expansion term is shown here, where we just expand our binomial between p and 1 minus p. We've already discussed that between the probability of something decaying, something not decaying. So if we have this and I differentiate with respect to x, well, this equation then falls out to be this equation here. And I see that it's just the sum of r from 0 to n, r x to the r minus 1 times the probability. Now if I take that equation and I just let x be equal to 1, this sum then gets converted into this equation. This is related to number and probability. And for radioactive decay, we use n naught and 1 minus e to the minus lambda t. So now we have a route to talk about what's our standard deviation that may occur for decay of a certain amount of radionuclides in a given period of time. Let's define another term here, m. M is the average number of atoms disintegrating in time t. And I can measure this as counts on a detector. So this is something that we can, and this is important because this is something that we'll do that we could do in the laboratory and use as data. M is going to equal to the n naught, the number of initial atoms, times e to the minus 1 minus e to the lambda t is this equation that's listed here. Usually lambda t is small, and this means that m winds up being equal to m is equal to n naught lambda t. And I can even use this to talk about rates. We have to talk about disintegration rates where it's counts per unit time, so counts per minute, counts per second. Well, the rate here is just nothing more than m divided by t, and that's equal to, if I look over here, I take this t divided by here, m equals n lambda, and this corresponds to our equation that we use frequently for determining activity, where the activity counts per second is equal to lambda n. Right, so we can use that information to talk about how we can derive a standard deviation for certain counts. And this standard deviation is just based upon the expected standard deviation from binomial distribution. So we'll use the binomial expansion, which again is shown here, and we'll differentiate that with respect to x. So this figure here, this equation here we talked about, it's at the bottom of slide 3-6, and I just differentiate with respect to x. So these equations, through the differentiation, get changed. And just like we did before, we set x equal to 1 and p plus p minus 1 is equal to 1. This equation then gets varied to here, where n times n minus 1 p squared is equal to r squared average minus r average. If we remember that variation, the sigma squared is equal to r squared average minus average r squared. That's our variation in our numbers. That's fundamentally the value that we're interested in trying to determine, this variation in our counts. We combine these equations together, and what we do, we get, from that we get the sigma squared is equal to n times n minus 1 p squared plus the average r minus the average of r squared. So we can now have a route for determining the standard deviation. And we solve this equation through using this relationship. The standard number of decays, or the average number of decays, is equal to n times p. This equation is expanded. It's squared, so we take the square root, and it just turns out to be the square root of np times 1 minus p. If I take this fundamental equation and I apply it to radioactive decay, what I get is a way of determining the standard deviation from the number of counts. So if we remember, we defined this earlier, that m is the number of counts, and I haven't expanded, or I just expand this equation, include terms that relate to radioactive decay. So sigma is equal to the square root of n naught times 1 minus e to the lambda t times e to the minus lambda t. Well, that's just equal to square root of m times e to the minus lambda t. In practice, count time is small, so lambda t is small compared to, so the count time is always much smaller than your half-life. So this term is approximately equal to 1. So your error is just equal to the square root of the number of counts. The relative error is just the inverse of that. So we can use this fact to answer an appropriate question. What is a reasonable number of counts to have in an experiment? The more counts I have, the lower the error. And here's an example. If I have counts of 10, 100, 1,000, 10,000, here's my relative error. So if I have 10 counts, it's really 10 plus or minus 3.1 counts. Those would be my average. 100 is 100 plus or minus 10. 1,000 is 1,000 plus or minus 31, etc. So that's my error in my counts. My relative error, as you can see, really decreases from 31% for 10 counts, 10% for 100 counts, a little over 3% for 1,000 counts, and if I'm at 10,000 counts, my error is on the order of 1%. So this kind of gives you an idea of what would be a good count rate for an experiment. And just through inspection, a count rate between 1,000 and 10,000 is going to give us pretty good error. We've already mentioned activity, and we showed how we generated this equation. Activity equals lambda n. Well, we know that the activity can be measured in the laboratory. Now, in our detector, not every decay is observed, so what we measure on a detector is counts. I have so many counts per second. And by knowing the efficiency of the detector, and it's usually at the energy that one is measuring the particle, you can determine activity. So by knowing the efficiency, if I have the counts, I divide that by the efficiency, I can get activity. And since activity is equal to the decay constant times n, and we already talked about this equation where the number of atoms at time t is equal to the number of initial atoms, e to the minus lambda t. Well, I can easily convert that equation to activity by just multiplying by the decay constant. So not only does the number of atoms, but activity holds for that. And one of the ways that we talk about activity units, we have two fundamental units. One is the Curie, which is defined as 3.7 times 10 to the 10th decays per second. And that's kind of a strange number, but it comes from 1 gram of radium-226. And as an exercise, if you were to use this equation, you can determine the activity of radium-226. So 1 gram, so that's 1 divided by 226 times Avogadro's number. That will give us n. And the decay constant, we'll just look up the half-life of radium-226, and I believe it's 1,600 years. You can use that, you get your decay constant. Taking those two numbers together, you should get 3.7 times 10 to the 10th decays per second. Now, becquerel is another unit where it's just 1 decay per second. So you may see units listed in Curie or in becquerel. Now, we've already discussed the decay constant, but here we can derive it and show how half-life comes into the decay constant. Now, we defined half-life as the amount of time that's needed to decrease radionuclides by 50%. The mass, the total number, doesn't matter. And here's our radioactive decay: 1 half-life, 2 half-lives, 3 half-lives. So we just see that the relative amount decreases by half at each step. So there's a relationship between the half-life and the decay constant. If we define n over n naught equal to 1/2, right? So we go from this point to this point. By definition, that's 1 half-life. So now T here is the half-life of that isotope. So we can take this equation and rearrange it, taking the log of both sides, where the log of 1/2 is equal to minus lambda half-life. Well, this would be the same thing as saying log of 2 is equal to lambda times the half-life. It took an inverse of this. Same here. and now the half-life is equal to log 2 divided by lambda, and this equation can be rearranged so that lambda is equal to log 2 divided by the half-life. Right, so one can measure half-lives, and the routes that you would use to measure half-lives depends upon the nature of the isotope. If you have a relatively short half-life, well, I can just perform an experiment where I measure at various times, and these times are larger than the half-life. So imagine if I was looking at the figure up here, and I took a measurement here, half of a half-life, 1 half-life, 1.5 half-lives, 2 half-lives. I'd be able to take my data, fit it on this curve, apply it to this equation, and solve for the half-life. Now what if I have a half-life that's very long? Let's say I have a half-life that's 1,000,000 years. Well, I can measure the half-life based upon the decay rate. So if I took a sample and I knew n, so I knew the mass of a sample, I know how many atoms were in that sample, and I measured its activity, A, I could rearrange this equation. Activity divided by n will give me lambda. Lambda is log 2 divided by the half-life. I can therefore find the half-life. Another equation that comes out of the exponential decay of radionuclides is the average lifetime. If we look at the figure here, we see that this decay follows first order. Now, we said that we cannot determine when a specific isotope, an atom, would decay, but we can talk about an average. If I look at the average lifetime for any isotope on this figure, half of them will have decayed within the first half-life. But there will be a small percentage that will be around after the fourth, fifth, etc. half-life. So there's always a small percentage of atoms that have many half-lives. So if I want to talk about a lifetime, I can use this value here, this equation, which is the opposite of 1 divided by the total number of atoms, where I integrate over time from 0 to infinity with respect to the number of atoms. This equation comes out to be, through this integral, just 1 over the decay constant, so 1 over log 2 divided by the half-life. So I can rearrange this equation, where I use the half-life directly, where the average lifetime is equal to about 1.4 times the half-life. So that says that the average atom will live about 1.5 times the half-life. Now this is important if you're doing atom-at-a-time chemistry. If you think about the idea of a half-life where something loses half the amount, if I only have one atom, that doesn't mean anything. I can't lose half of an atom. But what I can measure is the lifetime of that atom, and from that lifetime I can get the decay constant. From the decay constant I can get the half-life. The lifetime of an excited nuclear state through gamma decay also has a role in most power spectroscopy. This is due to the uncertainty principle, which relates energy and time. So we can just say time is a lifetime here, and we get a relationship between energy and that time. It's called this gamma term, which is the gamma decay width. It's fundamentally a resonance energy, and this gamma decay width you can evaluate with this straightforward equation here, which is just equal to 4.5 times 10 to the minus 16 divided by the half-life in seconds, and that gives you the energy of the width. And this says for things that are relatively short, you can have an energy that starts to become significant. Obviously with a second, that gamma decay width, the width of that line for the gamma decay, is on the order of 10 to the minus 16 eV, extremely small. If one has very short half-lives, then this width will increase, and this is useful in most power spectroscopy, where we can get a absorption, an emission line, and an absorption. These emissions are from gamma decay isotopes, and absorption are those compounds that contain the daughter isotope. So for instance, you may have americium-241 decaying to neptunium-237, the excited state, and a photon is emitted from that excited state. That's the source, and the sample has the neptunium-237 in it. This emission line, there's this energy distribution range shown here, E sub r, which can overlap between the emission and the absorber. What's shown here is the change of that overlap as a function of time, and the relationship between this E sub r term and the full width half max. The Doppler effect plus this resonance energy is about equal or a little bit greater than the E sub r term. So Mossbauer uses this, the fact that there's this short-lived gamma decay, coupled with the Heisenberg uncertainty principle, we have a large gamma decay width, to exploit this overlap between the emission and the absorption lines and use that to couple this electromagnetic property with the electromagnetic property of the atomic electrons, and uses that to determine something about the chemical state of the compound. So out of what we discussed, if you're going to remember anything, I would focus on this slide. There are a few equations here that are listed that provide basis for doing future work in radiochemistry. This is a workhorse equation, n at time t equals n naught e to the minus lambda t, where n is the number of nuclei, either initial or at time t. This is my decay constant, and t is time. It also works for activity or counts. Or if I converted n into grams, it would work for mass. Another important equation is the activity equals the decay constant times the number of atoms. This tells me my activity is a count rate, so counts per second is equal to the decay constant. The decay constant should be in inverse seconds times the number of atoms. And then this equation, the lifetime equation that we just went over. And then also a very important equation is one that describes error, where for m number of counts, the error is just equal to the square root of the number of counts. So for 100 counts, I could say my count rate is 100 plus or minus 10. The square root of 100 is 10. That's my standard deviation. So it works out that this is an important term for doing experiments. And those are the important equations. All right, let's utilize some of these equations in examples. So let's do something with this equation. N at time t equals n initial e to the minus lambda t. I have an isotope with an initial count rate listed here, 890 becquerel. Becquerel is 1 count per second. After 180 minutes, the count rate was found to be 750 becquerel. What's the half-life of the isotope? So let's put in our terms. This is NT. This is N naught. I counted it for 180 minutes. That's the T here. And I just need to solve for lambda. Here's this equation. We rearrange the equation, take the natural log of both sides, divided by 180 minutes. We get this term here. We get the decay constant, log 2, divided by the half-life is the decay constant. We solve here, and we see that the half-life, based upon this measurement, is 729.6 minutes. Okay, another example for a half-life calculation, and this is for something with a longer half-life. Imagine I have 0.15 gram of curium-248, and it has a measured alpha activity of 0.636 millicurie. Okay, what's the half-life of the curium-248? We utilize this equation, activity equals lambda n. So first we need to find activity. I said that it's 0.636 millicurie, so that's 0.636 times 10 to the third curie. Ci is our unit for curie. And I said that 3.7 times 10 to the 10th counts per second, or 3.7 times 10 to the 10th becquerel per curie. So this gives me the value in becquerels. So I now have A in a unit that is workable. It's counts per second. I find N if I have 150 grams times 248 grams of curium-248 is a mole times Avogadro's number. I get 3.64 times 10 to the 20th atoms of curium-248. So I have, this is N, this is A. Activity equals lambda N. I want to solve for the half-life. Activity divided by N equals lambda. I plug this equation in. I get my decay constant in seconds. I get my half-life in seconds listed here. Now the half-life is 1 times 10 to the 13th seconds, which isn't necessarily a handy unit to have, so I convert that to years, and I get 3.4 times 10 to the 5th years. We can also use these fundamental equations to determine something about what we would expect to see in the lab. So let's use activity equals lambda N to estimate what our count rate would be on a gamma detector. And we're interested in counting americium-241. It has a photon at 59 keV. We know that our detector, say we calibrated a detector, and our efficiency is 15.5% at 59 keV. What that means is that it only sees 15.5% of the photons at that energy. That's actually a pretty high efficiency. So if we had 75 micromoles of americium-241, what kind of count rate would we expect to see? So for the gammas, we know that the detector only sees 15.5% of the gammas, and then for every decay, the gamma branching is 35.9%. That means about 36% of the time when americium-241 decays, a photon is emitted. And we get that data from right here. This is from the table of the isotopes. So my counts are equal to this value here is my detector efficiency. This is my gamma yield, lambda N. I get a decay constant. Well, the half-life is 432.7 years. That comes out to a half-life of 1.37 times 10 to the 10th seconds. My decay constant is listed here, 5 times 10 to the minus 11 seconds. N is the number of moles. Excuse me, N is the number of atoms, and I get that from 75 micromoles. So 75 times 10 to the minus 6 moles times Avogadro's number gives me 4.5 times 10 to the 19th atoms. And I plug all these terms into the equation. And what this is really saying, N is my number of atoms, lambda is my decay constant. That's how many decays I see, right? Out of each one of these decays, 35.9% of the time it emits a photon, and at that photon energy, only 15.5% of those photons are observed. So this gives me what I would expect my counts to be. And that's a lot of counts. Here's an example of the decay scheme for americium-241 from the previous example, where we see the americium-241 decays down to this state, the 59.5 keV excited state. And here are two routes of getting the percentage that we showed on the other page. The one here where we take this value, multiply it by the multiplication factor, or something directly from the web where we can get the percentage directly. And one thing I do want to point out from here is that the actual transition, as shown here, is 85% of the time it goes to this excited state, but obviously the number of the de-excitations are not with the 59 keV photon, since that only occurs 35.9% of the time. The equation activity equals lambda n can also be used to derive something called the specific activity. The specific activity is that activity for a given amount of radionuclide. As a shorthand, some people often calculate the specific activity. For instance, 1 gram of plutonium-239 has a certain amount of activity. As an example, let's calculate the specific activity for radium-226. 1 gram of radium-226, that has a half-life of 1,599 years. 1 gram times how many moles per gram times Avogadro's number equals 2.66 times 10 to the 21st atoms of radium-226. The decay constant, well, let's get the half-life into seconds. 1,599 years is equal to 5 times 10 to the 10th seconds. The decay constant from this is equal to 1.37 times 10 to the minus 11 inverse seconds. So activity equals my lambda times the number of atoms, and it's equal to 3.7 times 10 to the 10th becquerel. That is the definition of a Curie, and that's where the Curie definition comes from. 1 gram of radium-226 is by definition a Curie, and that is 3.7 times 10 to the 10th decays per second. We can get specific activities as a function of mass for any isotope we're interested in. Here's the equation for curium-244. As we see, the half-life is 18 years. We do the same thing, 1 gram of curium-244, so many atoms. The half-life, let's get the half-life in the seconds, and log 2 divided by that. Activity equals lambda n. We can get a generalized equation for this, where the specific activity is for 1 gram is equal to this value divided by the isotope mass times the half-life. Now if we plot that out, we see that there's a linear relationship, except carbon-14 is living up over here. It's offline. And that's because I'm plotting as a function of mass, and most of my data here is for the actinides. So the mass and the moles are pretty consistent. So a better way of determining specific activity might be, as opposed to looking at mass, would be looking at moles. And specific activity per mole is evaluated here. And let's say per mole is equal to 6.02 times 10 to the 23rd, so we fixed n. The specific activity, as an example of iodine-129 with this half-life, we just rearrange our equation. We get this half-life into seconds. We get the decay constant into inverse seconds. Activity equals lambda n, and it's going to always be a mole. We get so much activity per unit mole. We can have a generalized equation with it's pretty straightforward, where we get a constant divided by the half-life, and I've even set this half-life in years, where the specific activity in becquerel per mole as a function of half-life of the isotope is listed here. So this equation can be utilized to quickly get to a specific activity for a mole of any isotope, as long as you know the half-life.
Another example of a calculation you can do is something called specific activity with a carrier. So imagine if we add a radioactive isotope to a stable isotope. If we know the activity of the radioactive isotope, we can calculate the concentration of the entire amount of that element, knowing that there's isotopes there that do not decay. As an example, imagine that 1 times 10 to the 6th becquerel of europium-152 is added to 1 millimole of stable europium. So let's calculate the specific activity of this europium. So we can get becquerels per gram. we would need to find the grams of europium. Well, we have so many millimoles times 151.96 grams per mole. Here's how many grams we get. We know that we have 1 times 10 to the 6 becquerels per gram. Now we have a calculation that says so many becquerels per gram. So if we ever use this as stock solution, perform an experiment, if we count the activity, we know how many total grams of europium are present. We can also use this to say, let's say you make this at the beginning of a graduate school career, towards the end, 5 years later. What's the specific activity? The half-life is 13 and a half years. So we have our initial activity, e to the minus lambda times t, 5 years. The activity has gone down from 6.5 to 5.1 times 10 to the 6 becquerel per gram. We've also evaluated lifetime equations, and here's an example of something that we can use for lifetime calculation. I did this when I was in graduate school. I worked on this isotope, Rutherfordium 162. It had a half-life of 65 seconds, so the question is, how long would the average atom live? And we would make this atom at a time, so this was important to know. We actually used this average lifetime as the basis for how often we'd need to perform experiments. So here's our half-life, 65 seconds. The lifetime is 1.4 times the half-life. So every 90 seconds is when we wound up performing the experiments, because that would be the average lifetime for any atom that we would make.
Our final comment on the first part of this lecture is on mixtures of radionuclides. Here's a figure of composite decay, where the red line shows the sum of the activity of 2 isotopes. We're not distinguishing by energy, we're just doing total counts, so we're plotting total counts versus time. And we can see that this data is really composed of 2 isotopes. One has a slope longer lived, which dominates at the longer times. We could use that slope, draw all the way back to the origin. We can actually plot that information so we can get the initial activity of the first part. The second isotope, the shorter lived isotope, dominates early. That slope is, the slope initially is dominated by the decay of the first isotope. We can actually take this intercept, the y-intercept here, subtract it from the total, and get the initial amount of the second isotope available. And fundamentally, we're just solving this equation. Any activity at time t is equal to the activity of isotope 1 plus the activity of isotope 2, which we can get the activity equals lambda n, solve for that. In fact, with this equation here, we expand the n at time t equation to say that the initial activity of 1 and the initial activity of isotope 2, expand that so that the initial activity e to the minus lambda t for isotope 1, initial activity e to the minus lambda t for isotope 2, we can solve both the initial activity and the decay constant through this curve. We come up with data that shows we have 2 decay constants, 2 separate half-lives, and from that we can get the initial activity that we see of each isotope. This concludes the first part of the lecture. Please comment on the blog, and the second lecture will be posted soon.